All right, so this next part is going to focus on solids, liquids, and gases and how these intermolecular forces play a role with each of those states. First, we're going to look at solids. Ionic solids are formed from positive and negative ions. They are held together by those electrostatic ionic forces, the attractions between the positive and negative ions. Your metallic solids are your metals. And remember I said that you could not group your metallic solids with London dispersion forces. And the reason why you're not able to do that is that the metal atoms are actually positive ions that have delocalized electrons surrounding them, what we call a sea of electrons. And so there's an attraction between those metal ions and their respective electrons. Molecular solids are going to either be like your diatomics or just your molecular compounds. They're structural units of molecule, and they are held together by those London dispersion forces or sometimes dipole-dipole or even hydrogen bonding, depending on the polarity and what atoms are present in their molecules. Your network covalent solids are going to be some of the strongest solids you can encounter. These actually do form physical covalent bonds between atoms. They can be formed in 2 or 3 dimensions, things like graphite or diamond or quartz. And so those electron pairs keep those molecules together as a solid more intact than they would if it was just intermolecular forces holding them together. And then amorphous is dealing more with your entropy side of things, glass, polyethylene, nylon. These are covalently bonded networks, but they don't have a consistent pattern that we see in the network covalence. And so that amorphous structure does help them withstand temperature changes a little easier, which is why we can use polyethylene to cook in your microwave, although we know now that we need to be a little more careful with that depending on the type you're using, and that or to store items in. And we know that glass is able to expand and contract due to temperature changes as a result of its amorphous structure. So solids can be crystalline or amorphous. When they're crystalline, they do have a definite pattern to them. Amorphous, they don't. Regardless of what type of solid you have, their motion is limited, and how they are joined together in that crystalline or amorphous structure is influenced by their intermolecular forces and how well they can pack together. So we're going to talk about crystalline solids first, your ionic, your molecular, and your atomic solids. With your ionic solids, the ions are making up your lattice structure. They are arranged very systematically to kind of minimize those repulsions, keep negative particles away from negative ions and positive ions away from other positive ions. You want to have negatives attracted to positive and vice versa. So we don't want those repulsive ones there nearly as much. Salt is a classic ionic solid. These solids have very low vapor pressures, which makes sense. They have super strong intermolecular forces to overcome, really high melting and boiling points. They do tend to be brittle due to the repulsions that will form when layers slide across other layers, and they are able to conduct electricity if their ions are mobile. So that's going to happen when they are in a melted form or when they are dissolved, when those electrons are dispersing throughout. Your molecular solids are your covalently bonded molecules. These are attracted to one another through IMFs that are not nearly as strong as what we see with our ionic solids. They are non-conductors. They do not conduct electricity well at all. Their valence electrons are held onto quite tightly. Some examples include sucrose, your diatomic molecules, your molecular elements, just covalent compounds in general, polymers, and large biomolecules like proteins. These polymers and large biomolecules can have some non-covalent interactions. They can take place between different molecules or even within their own molecule if there are different types of regions present within that molecule. What types of properties they have do depend on their shape, and that's going to be determined in large part by their interactions, either within themselves or between molecules that are nearby. Atomic solids are going to have atoms make up the lattice structure. With your metallic solids, again, you can have metallic bonding occur, where these atoms are basically positive metal ions that are surrounded by lots and lots of delocalized valence electrons. And because these electrons are free, they are excellent electrical conductors, and they can be easily shaped. They're very malleable, and they can be drawn into a thin wire. They're ductile. Network solids are only going to be formed between your nonmetals. Again, physical covalent bonds, intramolecular forces are formed with these network solids that allow them to form large units that can have multiple dimensions. They tend to be very rigid. They're not going to change shape easily. They do not conduct heat or electricity well. We see them in carbon in the form of diamond and graphite. Silicon dioxide is another example, silicon carbide, as well as boron. And then the other atomic solid we're going to look at are your noble gas solids, group 8A solids. Excuse me. These noble gas atoms are attracted to one another via those very weak London dispersion forces. Again, the larger the noble gas atoms are with their number of electrons, the more of these London dispersion forces are likely to form. Alloys are mixtures of two or more elements, primarily metals, but they don't have to be just metals. This is going to help to give them greater strength and be able to resist chemical oxidation, corrosion. Two types of alloys we're going to look at are interstitial and substitutional. Interstitial is when you have an alloy made of atoms that have different sized radii. So the smaller atoms take up these interstitial spaces that are found between the larger atoms. Steel is one example of this, where carbon atoms basically get fit in between the iron atoms. The substitutional alloys are between atoms that have similar radii, and you basically just substitute one atom for another in the lattice structure. So with brass alloys, we can see this happen sometimes with zinc and copper. I already talked about amorphous structures. Again, glass is the key example typically with amorphous, that there's just a lot of entropy in their structure that can allow them not to keep a necessarily set shape, so rigid. So that was solids. Liquids, their particles are close together still, but not as close as they were with solids. They are in constant motion and forming collisions with one another. So their arrangement and their movement are determined in large part by the types of intermolecular forces that are present, the strength of those forces, as well as just their polarity and the kinds of bonds they can form and the temperature at which these molecules are found. Gases, as we just got done talking about, are in constant motion. Their collision frequency and their spacing is dependent on the other properties of a gas, its temperature, its pressure, and its volume. Because they are in constant motion, and because the forces that exist aren't attracted or are repelled by one another between the particles, they do not have a definite shape or volume. So the first question I have for you is, what type of solid will each of these form? So diamond is going to be made of carbon covalently bonded to one another, so that's network covalent. NBr3 is nonmetals that are coming together, and that's going to be a polar molecule because the nitrogen will have a lone electron pair if you draw it out. It's a molecular substance, a molecular solid. Hydrogen is also a molecular solid because it is the same element, but there are two atoms bonded together. Magnesium is a metal, so that's going to be an atomic metallic solid. KCl is a metal and a nonmetal, that would be an ionic solid. SF2 is made of two nonmetals, so that would be a molecular solid. That too has some polarity to it, so it would have dipole-dipole forces present. Argon is just that element. It's nonpolar, it just has London dispersion, and it specifically is a part of atomic group 8A. And then we have glucose. Glucose is made of just nonmetals, and it definitely has some parts that are sharing things a little bit differently than the other, which is why we're going to see sugar can dissolve in water pretty reasonably, but this would be classified as a molecular solid. So next I ask you how alloys differ from pure solids. Alloys are mixtures of metals, and so they are not pure substances. They can have the same radii or they can have different radii. While solids, pure solids, are made just from pure substances, either the same types and combinations of ions or atoms or even molecules. When you have an alloy, by having these different combinations of metals, they are going to be stronger and they are going to be more capable of preventing oxidation. They are less likely to undergo corrosion. And then I ask you, what type of solids are typically good conductors of electricity and heat? Your ionic solids are going to be good conductors because they have those positive and negative ions that are going to allow the electrons to flow through them. Same thing with metallic due to that sea of electrons, and the alloys being made of metals will also be able to do that. And then the last question I believe I ask you is, how do atomic solids differ from one another? They can differ in terms of their composition, what's making them up. They can differ in terms of the types of intermolecular forces or types of interactions in general that are holding them together. Whether or not they can conduct heat or electricity. We only see this with the metals.